Now we know that electromagnetic waves come in energy packets called photons, and photons carry momentum h bar k. So the energy of a photon is h nu, where nu is the frequency, h is the Planck's constant, or h bar w. H bar is reduced Planck's constant, h divided by 2 pi. Omega is 2 pi nu. Or hc over lambda, where c is the speed of light and lambda is the wavelength. Now, similar to electromagnetic waves, we can talk about quantization of elastic waves, and they are quantized in energy packets of h bar omega as well, and we call them phonons instead of photons. Now, when we say that the energy is n h bar omega, that means we have n phonons occupying this energy. So from quantum mechanics, the harmonic oscillator energy is quantized, and since we have arrived at the normal modes of lattice vibrations by considering the atoms as harmonic oscillators, the energy of the normal modes are, this is the quantum harmonic oscillator, n plus 1 half h bar omega, and n is an integer that goes from 0 to infinity. So n plus 1 half h bar omega are the energy levels of the quantum harmonic oscillator. At absolute zero, the normal modes will have a 0-point quantum energy h bar omega over 2. So none of these normal modes are occupied. We will have a 0 Kelvin atomic vibrational energy h bar omega over 2. This is basically due to Heisenberg's uncertainty principle. Now suppose that we add energy to a vibrational mode with frequency omega at one end. The smallest energy we can add, so energy packets are in units of h bar omega. So this packet of energy will travel through the crystal with a group velocity. Group velocity, remember, is d omega dk. So that's the propagation speed of the energy. Now, because the energy of possible modes are equally spaced with the energy difference h bar omega, the particle interpretation is given to the energies of normal modes, and n is called the number of phonons. So when we say that the energy is n h bar omega, neglecting 0 point, and this omega, remember, depends on the branch. So it could be optical branch, acoustical branch, longitudinal or transverse. So there is a branch index here. The mode is occupied by n phonons. N is called the occupation number. So we consider a normal vibration, a e to the ikx minus omega t. The energy of this mode averaged over time is 1 half m omega square a square, or 1 half c x max square, and omega is square root c over m. These are all from harmonic oscillator. In the quantum mechanical case, we have n plus 1 half h bar omega. So this is basically our Vmax in the maximum speed of the harmonic oscillator. So we have two results. Classical result, 1 half m omega square a square, and quantum mechanical result, n plus 1 half h bar omega. So if you look at the energy versus the amplitude, we have it's proportional to a square, so we have a parabolic curve here. But in quantum mechanical case, these are basically quantized, and the energy difference, delta E, as you can see here, is h bar omega. So 0 point quantum energy is h bar omega over 2, and then 3 over 2 and 5 over 2, etc. So the momentum of a quantum particle is given by the de Broglie relation. P is equal to h over lambda times k hat. If you divide it by 2 pi and multiply it by 2 pi, you find that it's also h bar k. So in analogy, we say that the phonon has a crystal momentum h bar k. So we were talking about photons carrying energy h bar nu, momentum h bar k. So we have a similar situation for phonons. They also carry a crystal momentum h bar k. So one thing we have to be careful about here, this momentum is not the momentum of the vibrating atoms, because if you look at the momentum of the vibrating atoms, that's time average is 0. However, this enters the conservation laws as a real momentum. So when we talk about creation or annihilation of phonons, this basically enters the conservation of momentum as a real momentum. So let's talk about this phonon momentum. So I said that the actual momentum of the vibrating atoms should be 0. So if you look at the total momentum of the crystal in the monatomic case, it is m dus dt summed over all atoms. So m d dt of us, and us is basically the displacement from equilibrium of the s atom, u0 e to the minus I omega t e to the ikas. So if I take its derivative, I find minus I omega us. So the momentum is then minus m I omega u0 e to the minus I omega t. Now sum over all atoms, s equals 0 to n minus 1 e to the ikas. So what is e to the ikas? E to the ikas is something that is less than 1. So if you look at this series, s equals 0 to n minus 1 x to the s, where x is less than 1, this is 1 minus x to the n divided by 1 minus x. It's geometric series. So we can use this mathematical relationship in order to find this sum. So this is from geometric series. That's what we note. Okay, so x is e to the ika, so that is going to give us 1 minus e to the ika to the power n divided by 1 minus e to the ika. Now e to the ika n is equal to 1 because k is 2 pi over na, 2 pi n over na, remember. So we obtain e to the I 2 pi, which is 1. So 1 minus 1 gives us 0, therefore the total momentum of the crystal due to vibrations is going to be 0. However, there is an exception for small k when k goes to 0. So if you look at e to the ikan behavior as k goes to 0, Taylor series expansion, that gives us e to the I0 for the first term. First derivative, ian e to the I0 k minus 0. So 1 plus e to the ikan. So for the momentum, we will have minus I m omega u0 e to the minus I omega t. Now, instead of this series here, we're going to have 1 minus, for e to the ikan, we will substitute 1 plus ikan. So 1 minus ikan divided by 1 minus e to the ika. E to the ika is similarly 1 plus ika for the small k limit. So these ones will cancel, and I will find that the momentum is minus I m omega u0 capital N e to the minus I omega t. So for the acoustical mode, as k goes to 0, w goes to 0, so we will find that this momentum is 0. But for k equals to 0, the original equation of motion admits another solution. So that's not the acoustical mode solution. So if I go back to the equation of motion for the generalized case where I have the interaction between the s atom and s plus pth atom, remember that the equation of motion can be written in this form where p is positive, and we assume a general solution with omega equals to 0, so there's no oscillation, or the time dependence is in u0 of t. So u0 of t e to the ikas, so I don't have the explicit e to the minus I omega t here. So if you substitute this, the second derivative gives us, because the time dependence is hidden in u0, d square u0 dt square, this is equal to sum over pcp, and for us plus p, I will have us e to the ikap minus us. So if I write us is u0 e to the ikas, I can take these into the e to the ikas parentheses, and e to the ikas's will cancel, and I obtain md square u0 dt square is sum over pcp u0 e to the ikap minus 1. When k is not equal to 0, we get e to the minus I omega t as solutions before, but when k is equal to 0, e to the I 0, that's 1, 1 minus 1, so the right hand side is 0, md square us dt square is 0. This has a solution at plus b. So that's a constant velocity solution, which is a uniform motion. So the momentum of the crystal then will be capital M sum over s dus dt, capital M sum over s e to the ikas du0 dt. So du0 dt is a for this solution. So that's the derivative. So I will find that m sum over s a at k is equal to 0, which is the total mass times velocity. So basically this tells us when k is equal to 0, it's the rigid body motion of the crystal. The crystal moves as a whole with constant speed. A is a solution. So that's not so surprising. Okay, so but for practical purposes, we find that when a phonon interacts with other quantum particles, it behaves as if it had a momentum h bar k. So we call it the crystal momentum of the phonon, but when you look at the actual momentum of the crystal, as we have discussed here, its actual momentum is going to be 0. Due to oscillations of the atoms. There is one exception for k equals 0 when we have uniform motion of the whole crystal. So when we consider elastic scattering of X-rays, we have for low diffraction condition, delta k is equal to g. So basically k prime is k plus g. This is also true for elastic scattering of a phonon. In the reflection process, conservation of momentum dictates h bar delta k must be equal to h bar times g. So the crystal has to recoil with a momentum minus h bar g. So this appears as if we have a momentum conservation. So delta k is equal to g is basically a momentum conservation equation. So if you have an incoming phonon with momentum h bar k, scattered phonon h bar k prime, that delta h bar delta k must be equal to h bar times a reciprocal lattice vector. So this basically equation written in this form, the incoming phonon momentum, scattered phonon momentum, and crystal momentum, as you can see, is minus h bar g. This should add up to 0. So there's the recoil momentum of the crystal. Okay. So if the scattering phonon is, the scattering process is inelastic, then either we will have a phonon created or absorbed in the process. So if you look at the momentum conservation, k is equal to k prime, scattered phonon, minus g plus or minus q. So we will have q, the wave vector of the phonon. If it's positive, it's created. If it's negative, it's absorbed. So the momentum h bar q is actually given to or taken from the crystal. So that's basically what it is describing. In order to find the phonon dispersion relation for the jth branch, omega j of k, we can use inelastic neutron scattering. So that then we need to consider interaction of neutrons with phonons. If the incident neutron has energy h bar square k square over 2 mass of the neutron, scattered neutron has energy h bar square k prime square over 2 mass of the neutron, then if you write the energy conservation, h bar square k square over 2 mn is equal to h bar square k prime squared over 2 mn plus or minus h bar omega. A phonon is created or annihilated. And you have the momentum conservation, k is equal to k prime minus g plus or minus q. That's momentum, a phonon created or annihilated. So if we scan directions to check when the selection rule is satisfied for phonons, we can determine the q vector of the phonon. So therefore this gives us basically omega as a function of k relationship using inelastic neutron scattering. So we talked about the quasi-particles that describe elastic waves. These are called phonons. They have energy h bar omega. If we find that a mode has energy n h bar omega, we say that it's occupied by n phonons. The 0-point quantum energy of the harmonic oscillator is h bar omega over 2. And when we have the classical harmonic oscillator compared to the quantum harmonic oscillator, we see these discrete levels with energy differences h bar omega. The phonon behaves when interacting with other quantum particles as if it has a momentum called the crystal momentum of the phonon h bar k, but the actual momentum of the crystal is normally zero due to vibrations, as we have shown here. However, there is one case when k is equal to zero, that is the constant velocity uniform motion of the crystal, that is when it is non-zero. Okay, so when we look at the momentum conservation when interacting with other quantum particles, for example, for X-rays, we have delta k is equal to g. This basically describes to us that if you multiply this equation by h bar, in the process, the crystal has to recoil with a momentum minus h bar g. So this is true also for phonons. When you have a phonon coming with momentum h bar k, scattered phonon h bar k prime, the change in the momentum must be h bar times a reciprocal lattice vector g. If in the scattering process a phonon is created or annihilated, we won't have energy conservation. This would be an inelastic scattering of a phonon, where h bar q would correspond to the momentum that is taken or given to the crystal. In order to find the dispersion relation for a phonon for the jth branch, we can use inelastic neutron scattering, and we can write the selection rules here. The energy conservation gives us the loss in the energy of a neutron must be equal to a multiple of h bar omega, the phonons that we're creating. So for one neutron, we create one phonon, or we annihilate one phonon. And we can see that the momentum conservation tells us that there's a plus q or minus q for the incoming neutron turning into the scattered neutron with a wave vector k prime, and there is the recoil momentum minus g. So if we scan the directions to determine under which condition we will have this selection rule being satisfied, we can determine also the direction of q of the phonon. So this will give us omega as a function of k using inelastic neutron scattering.